All right. Thank you everyone for signing on for lecture 11, where we will be talking about logistic regression. So the overview of what we've done so far is we've looked at linear models, we've looked at smoothers, we've looked at this whole setting where x is real valued, y is real valued, and we want to predict x from y. Now, in a lot of cases in real life, why we might want to predict discrete outcomes. The simplest case being yes or no for a particular question given some data. So if you're given data on a patient, does this patient have common cold or not? It's a simple yes or no outcome. Um, I'm going to say it's always nice to have uncertainties along with that yes and no answer, just to have a well calibrated model. But I'm getting ahead of myself. So the overview is like if your doctor tells you you have a disease and also adds that it's 70% likely or 50% likely, you have, it's a huge difference between saying I'm 99% sure you have this disease versus I'm 50% sure. So that yes or no also has this variance between it. And it's nice to have uncertainty, but we don't always have it. So logistic regression is basically about the discrete outcome. And I brought up the point about uncertainty just to add on to that and say, like, why is this idea of uncertainty is important? But yeah, so to start off, like now, why is discrete? We want y to be discrete, and therefore this reduces to a classification problem. Let me move this out just in case. Um, yeah, so that is that. So what would be nice would be to have the conditional distribution of the response y given the input variables. And like I said, the idea of uncertainties, it would be nice to have that, but it can be hard because while in order to obtain this conditional, there is a joint distribution that has to be modeled, and that is hard for high dimensional data. So to put it very simply, let's I can start with a question. How do you turn a continuous random variable into a binary one? You can feel free to unmute and answer.
Sigmoid.
Sigmoid.
Other.
So I'm thinking of something even simpler.
Okay.
Like one
Maybe
way, so yeah,
step
sorry.
function or some, maybe sort of step function or something like that. Whether if it's something like above this value, but yeah, I don't like.
Yeah, as a matter of fact, I was thinking of like a simple threshold, so a step function where I fix if this is my graph, so I use u instead of y just for generality and not confusing you with notation. For my variable u, which takes a certain distribution of values. So this thing, um, I want to just set a threshold u naught where I say, okay, if it is below u naught, then I will just return 0. And if it is above u naught, I will return 1. And that sort of function that we define with this continuous random variable is called an indicator function or indicator random variable, where we say that this indicates whether the condition written below it, this condition, is true or false, and accordingly returns either 0 or it returns 1, right? And if you examine this indicator random variable, like we've discussed before, when you have a random variable, you want to define some sort of summary statistics for the set of values that it takes. Oops. And if you go to define this expectation of this indicator random variable, you remember that expectation is equal to the value times the probability of that value. So this notation, integral x times px dx. In the discrete case, this reduces to sum over the values that it takes, the values times the probability of those values, which is exactly what I'm doing here, taking the values times the probability of the value. Okay. And as we can see, that results in 1 time probability of u greater than u naught plus 0 times probability of u less than u naught. And 1 times this is just this. But now if we go back to the graph, probability of u is greater than u naught, which is this thing, is basically just probability of u is equal to 1. And if we define y to be a transform of this random variable, so then we can just say this is equal to probability y is equal to 1, which is what they want us to show here. Okay, so let's just undo that. Okay, very good. So in a line, conditional probability is the conditional expectation of the indicator. This helps because by this point we know all about estimating conditional expectations, right? So the most straightforward thing to do at this point is just to pick a favorite smoother and estimate the regression for this indicator variable, this y is equal to 1 thing. And we know how to do that. You know that there is this loss function. You want to minimize this loss function. You have maximum likelihood estimation. So there are now when you talk about maximum likelihood, um, one thing that is worth mentioning is that actually it'll come up later. So let me not get ahead of myself. There is, I guess it comes up right now. So, with maximum likelihood, you run into this problem where you know that your probabilities must be between 0 and let's say yeah, to step back, like you want to regress your x on your indicator variable, and the easiest way that we've already seen to do that is to use a linear regression. And the reason that we can't just dump our data into a regression model is because it will still predict some value of y from some value of x, but there is no reason that this value will belong to 0 1. I should write this. There is no reason, like you're not constraining this, so it could predict a y that is 10 or like 5.9 or minus 1.2, um, even though your data might be belonging to 0 1. So in order to enforce this constraint, we must need to do something. Hopefully that's clear. If as with all the lectures, if at any point there are questions, just interrupt me, stop me right there, and I will take the time to explain it again. You can unmute yourselves whenever you feel like it. So that's issue number one. Secondly, we are trying to estimate probabilities. So um, you know that it takes the value 1 and 0 with a particular probability that has to do with this x. So you might as well just model the probabilities. And there is a reason that he gives the motivation for why we need to model the probabilities, where he says that if you don't model, and by model you mean you consider the probabilities as a function of x given this theta is the parameters. So we'll see. Yeah, so this is called modeling the probability, as opposed to just taking a pi, p of xi comma theta. So as opposed to just taking this value, this would be called making a model for the probability. So he says we are better off doing this than this, and he motivates that by saying, okay, recall that in a sequence of Bernoulli trials, there is a constant probability of success, where there is a constant probability of success p. So now he's just taking p. Um, um, you obtain this sort of model for likelihood. And you know that this model is maximized when p is equal to the observed. So in a coin flip, if you observe 55 heads, then you take the probability as 0.55 probability of heads. You're basically doing 1 by n times summation of yi, because yi can only be 0 or 1. And so just summing this up gives you the probability of the ones. So yi is equal to 1 is equal to 1 by n times summation of 1, however many time 1 occurred in those 1 to 100 trials. Hopefully that's clear. So that's all that this is saying. So typically, this likelihood is maximized when you take this estimate of your probability, but there is a problem with this. And what is the problem? The problem is if you try to maximize the likelihood without any constraints, then you're going to get pi is equal to 1 for heads and pi is equal to 0 for tails. And you're not learning anything. Like if you multiply it together, you're still going to get like let me be clear. um I wrote this down. So I think what this means is we cannot model a per data point success probability because that leads to no learning. Instead we model it as pi is equal to p of xi given theta. Thus we have a valid mle problem. So the reason this is an invalid mle problem is because you're going to learn a deterministic value of p that is not a function of x, and that deterministic value is going to fluctuate between 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, that sort of thing. And it's not going to be any real learning. At least that's what I think this means. If I'm wrong, then please correct me. And this is because we're modeling it as an inhomogeneous Bernoulli, which means each trial has its own success probability pi. So there is no global model for the probability. There is just each data point is being, you're maximizing the likelihood of each data point. Um, anyway, so if on the other hand, we assume that pi are not just arbitrary numbers, but are linked together. That is, if we model the probabilities, these constraints give non-trivial parameter estimates. So these are trivial parameter estimates because it's just 1 and 0. But now we want to obtain a non-trivial parameter estimate, which actually means something. So in that, we impose this constraint on the model. And again, this is an assumption we are making. So think of it that way. So we are assuming that this p is a function of x because if we don't, then we can't do anything, right? And so similar values of xi must lead to similar values of pi. I mean, fair enough, it's a function, right? So similar arguments to the function should lead to similar probabilities. Then we obtain this likelihood as a function of theta as opposed to this function of this pi. Um, and so that then gives us a valid MLE problem. That's what I'm talking about here. Okay, so what we've described is right now we have a binary output variable y. So remember that this is no longer y is like now a binary output variable, not real valued. And the goal is to model the conditional probability of y is equal to 1 given x is equal to x. And y is equal to 1 because we're just assuming two classes, a binary output variable. So yeah, if you have probability of y is equal to 1, then it's just 1 minus probability of y is equal to 1 given x equal to probability of y is equal to 0 given x. So this gives you the complete model, just knowledge of this much, right? That's all they're saying here. Okay, so by now it will not surprise you to learn that statisticians have approached this problem by asking themselves, how can we use linear regression to solve this? It's the simplest model, it's reasonably interpretable, why not just try and use it to solve a new problem? Okay, most obvious idea is to let px be a linear function of x, right? So if you're assuming a model, assume the simplest possible model. Every increment of x, of a component of x, would add or subtract some amount to the probability. So the conceptual problem here is that p must be between 0 and 1, and linear functions are unbounded. So a linear function is just going to go like, sorry, if I impose this constraint of this x-axis is the variable x, and this is p of x given theta. Now I want my probability to be bounded between this interval 0 and 1 for it to be a valid probability. But any linear function, no matter what slope I give it, as long as it is not, sorry, as long as the slope is non-zero, it's going to keep going up or keep going down on either end. And so it's not going to result in a valid probability model. The second problem with this is, like, in a linear model, there is this concept of diminishing returns that is not satisfied. So diminishing return means when you go at like higher or lower values at the extremes, it changes far slowly than at the central points, or what, at smaller x. So change the idea of diminishing returns is changing p by the same amount requires a bigger change in x when p is already large. So p is not changing here, p is changing only by this much, whereas here p is changing by this much. So when p is already large, or um, um, it's harder to change p, like you need more of a change in x compared to this. Okay, that's this idea of diminishing returns. Okay, don't want that. Okay, cool. So second problem, right? Linear models can't handle diminishing returns, and diminishing returns is an empirical thing. Um, and it's interesting that he uses this to motivate the idea of a logistic transformation. So the natural next step is to use a log function, but a log function is unbounded on the bottom, although it goes up like this. Um, um, what do I want to say about this? Log 0 is 1. No, sorry, I wasn't talking about that. What I want to say about this is that you need to bound it on the other end also. And so you come up with this transformation log p over 1 minus p. And he motivates this as the natural next thing to do, which means, like, for different problems, you can model this function differently. Like, you don't have to use the exact same function. And that sounded interesting to me because that is one way to motivate all of these squashing functions that um, uh, activation functions, I believe they're called. But anyway, so again, it is another assumption that we are making. It is not necessarily the right one, but it is an assumption that makes life a bit easier. So um, assuming this, because remember p is a function of x and theta. Now theta is our betas. So given the parameters, this is the model for p. And solving for that, you obtain p of x given beta of this form, which, if you recall, you will have seen in machine learning as a logistic function. Okay, now he makes a general point about the probabilities changing much faster inside the domain. So if you have data points A and B, again, you haven't labeled them yet. So basically, these are just all X's. Once you make a decision boundary, this is technically just like X, 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 X. Once I make this decision boundary, then I say, okay, on one side, these are all A's, and on the other side, they are all B's. So after that, I have my labels. And what he's saying is that these labels have these the probabilities, the class probabilities depend on the distance from the boundary in a particular way, and that they go towards the extremes far more rapidly when the mod beta is larger. So mod beta is the norm of your parameters. And he illustrates this point through this diagram, where again, these are the same data. So these are the same x's. It's just that based on your classifier, he's labeling the data. So based on your logistic regression, you obtain your class labels. which gives you the pluses and minuses. So all of these have the exact same data points. It's just the labels that are changing. And he's saying that as you increase the norm of your parameters, you get clearer decision boundaries. So the decision boundaries here are all over the place, here less all over the place, less all over the place, and the best ones. So yeah, evidently increasing the parameters gives you increasing the norm of the parameters makes the probabilities go to zero, go to the extremes faster. I don't know like exactly why he made that point there, because like I guess just as like a note to remember. But okay, cool. So it is one of the most commonly used tools, logistic regression. And there are four reasons for this. One is tradition. You go from linear to logistic. The other one is this log p by 1 minus p actually is an interpretable term called the log odds, which is obtainable like in a sense by taking um, remember when we said this 1 by n summation y I think basically if you have a table of like um, experiment, so coin flip, coin flip, coin flip, coin flip, and you have heads and tails, and you have this was a tails, this was a heads, this was a heads, and so on. Then the log odds are just like summing this column and summing this column, and it's like easily interpretable. um, and logistic regression is just this idea of, okay, if I had infinite rows, then how would I obtain this? And so you can get like an empirical estimate of these log odds through this table, and it just makes life easier. That's, I guess, what he's saying. Um, okay. Um, yeah, classification is a bit like having a contingency table and infinitely many rows. We can estimate the log odds empirically just by taking the counts. And with infinitely many rows, we need some sort of interpolation scheme. Remember that interpolation was just if you have 2 points, then trying to join this with different lines. If you have 3 points and trying to join this with different lines, it's interpolating between them. Anyway, that's another. Yeah. So now that we come to a super important point, which has to do with this exponential family of distribution. So a logistic regression is closely related to this exponential model, exponential family, where the probability of some vector v is proportional to exponential beta naught plus summation over some function of v times beta j. So some vector v is proportional to the probability. So pv is proportional to exponential some constant plus some function of v times some other constant. And why is this format important, like this exponent raised to some function of v plus something? This is important because a large class of distributions can be expressed with this formulation. And I'll get into some more detail about it because exponential families are super, super interesting. They arise in many contexts in statistical theory and physics. So there are lots of problems which can be turned into logistic regression. So, okay. Now this idea of exponential families comes from the 1930s, specifically 1935, 36, where someone said, okay, we have all these distributions, like let's posit a general class of like a canonical way to express these distributions. So most of the distributions that were discussed, your Bernoulli, your normal distribution, your geometric, um, your Poisson, your, I don't know if you guys have heard of inverse Wishart and Wishart, but like lots of distributions can be framed in the form of an exponential family. And why does that matter? Well, because they have certain nice properties. One of the very important properties is exponential families have conjugate distributions, which means if you have a, and this goes back to some part of Bayesian machine learning, where if you have a prior, sorry, You want to calculate the posterior over your data, posterior of your, again, I don't know if I should be getting into this. Posterior is proportional to prior times likelihood. And the idea with your posterior, so okay, so let me break this down more. So a prior is your thought process or understanding without any data. So just like, and I gave this example when I was explaining this in the office hours and it worked out. So let's reuse it. I know without any knowledge that onions and milk won't make great chocolate. Um, and I want to posit some models to make chocolate and see like what my data tells me, and that's under my model. That's my data likelihood. And if the data shows that like, well, it turns out if you fry onions and put them with cream and stuff like that, and it turns out to make really good spicy chocolate, then my posterior will tell me, well, you were wrong. Onions and milk make good chocolate. And the real problem in solving this, is there is a this to make this proportionality into equal, there is a normalizing constant that has to be computed, and that is super hard to compute because that has to integrate over the space of all models, and that is not easily doable, especially when you get into even a slightly complicated problem. So, long story short, exponential families have this property where if you have these conjugate distributions, then multiplying your prior times your likelihood will give you a closed form solution for your posterior. So you can actually write it down and compute it by hand. And that is super, super useful. Because essentially like closed form was, remember, for linear regression, our closed form solution for the OLS estimator was X transpose X inverse X transpose Y. So you just need to plug in these values and voila, you have your beta star. So similarly, imagine like solving these complex Bayesian inference problems just by plugging in some values and like obtaining an answer. It's magic. So that's why this idea of exponential family is super important, because they have, among other properties, this is one of them. And of course, there's some restrictions, and I'm oversimplifying things, but that's mainly because like we haven't really discussed Bayesian inference before. Um, but yeah, you start with a prior, you um, get some data likelihood under your model, and that gives you the posterior. That's basically it. Hmm. Okay. So the general form, the canonical form for an exponential family is this one, and we'll get into what this means. So it says f of x given theta is equal to h of x times exponential eta of theta times t of x plus a of theta. So what is this form, and like why do we care? Well, h of x is some function of x, clearly. This has to be, so because this is a probability distribution, this has to be a non-negative function because exponents are always going to be non-negative. Like e raised to x, no matter what x is, this will be 0 or greater than 0. Um, Sorry, I shouldn't say 0. Um, yeah, that is the e raised to x belongs to 0 comma infinity, right? Yep. And that's why this thing cannot be negative, because then this function will be negative and then it won't be a valid probability density function. So yeah, non-negative function. What is this eta of theta? It's just it's called a natural parameter. That's all you really need to care about. Um, I'm not going to go into these details because like that's not what the chapter is about, but this is used in a lot of machine learning stuff, and this idea of particularly in the Bayesian setup, you have exponential families playing a really nice role. T of x is sufficient statistic. This we know of. This we use to summarize our data. Important to mention IID. And a of theta is this the normalizing function, like that normalizes this to be a valid probability distribution. So, and we'll see what I mean by that with through an example. So it's also called the cumulant generating function. More on that later. Actually, not in the lecture, but yeah, you can read up about that, like what that means. Now, we said the canonical form, and we said that all of these families, in addition to more, can be expressed in this canonical form. So what does this mean? I'll take the normal distribution, for example, normal of x given theta, where now you know that your parameters are equal to this, actually written it down. Your parameters are actually equal to mu and sigma. Okay. Your parameters are equal to mu and sigma. You know that this is the form 1 by 2 pi sigma square exponent x minus mu the whole square by 2 sigma square. So I just expanded it out, a plus b the whole square time whole times minus 1, right? So minus a square plus 2ab minus b square. Okay. And if you want to make this correspond to this, well, sorry, not, I mean this entire expression, if you want it to correspond to this, how you factorize it is basically you obtain your um, t of x times eta of theta. So eta of theta cannot be a function of x, and t cannot be a function of the rest. So you obtain t of x as x square, this vector transpose, and you obtain eta as this transpose, or this, I guess, I don't know. And when you multiply these two vectors, you obtain mu by sigma square times x. So mu by sigma square times x, the two cancels out, and you get minus 1 by 2 sigma square times x square. Okay. So minus, where is minus 1 by 2 sigma square times x square. Fair. Finally, what is remaining is your moment generating function. And remember that we have this is a function of x, right? Hx is a function of x, so it can just be a function of x that actually doesn't, that has x raised to 0. So that basically that way, x raised to 0 is 1. So it is a function of x technically. It's just a constant function. And it cannot be a function of the parameters because it's not, there's no theta here. So that means this square root of sigma square goes up as like log sigma square, log mod sigma. And that's where this thing comes from. So we push this term into the exponent in order to get this normalizing constant. And you can see that because of this formulation, you have now your parameters, and you have your canonical form for the normal distribution. Um, I'll pause here if there are any questions. Yeah. Okay. Seeing none, let's move forward. Why is it always 9:41 a.m.? I don't understand this. Hmm. Okay, or maybe a bug, but okay. So, finally, the last thing I want to say is like logistic regression is used because it often works surprisingly well as a classifier. I mean, it's like it's not really, it works correctly, but it works well. So even though like the true model might not be linear, uh, a logistic regression gives you a good approximation to it. Okay, so the likelihood function that we discussed, if p is a function of x, then this p raised to y times 1 minus p raised to 1 minus y reduces to this thing, p of x now, as opposed to just p. And it's really p of x and theta, where theta is beta naught and beta, but like they abstract that away for you. And if you take the log likelihood, then it turns into this form, which if you substitute now the value of px, you obtain this form, this final one. Yeah, nothing much to say about that. Then if you want to do your maximum likelihood estimate, you differentiate with respect to your parameters. But as it turns out, that results in a transcendental equation, which means an equation with a transcendental function. A transcendental function means there is not a solution possible within finite steps of algebraic operations, so plus, minus, divide, whatever. So there is no closed form solution for this little boy, girl, whatever. This little equation has no closed form solution, and so we need to do something that is better than maximum likelihood estimation in the that we do by taking derivatives and setting them to zero. And that better thing is called numerical optimization, which means we are again approximating this through numerical methods, through stochastic methods to be precise. So what it says is in standard gradient descent, you take the gradient and you move in the direction of the gradient, the reverse direction of the gradient. Now what Newton's method does is, instead of just the gradient, like I also want to know how fast is the gradient changing. So like if my gradient changes very slowly, I'm probably somewhere here, so I want to take small steps. Whereas if my gradient is changing very fast, then I'm probably somewhere here, and I want to take large steps to get to this place where my gradient changes very slowly. That's the idea. So Newton's method takes second order derivatives, starts with an initial guess, then calculates the gradient of the log likelihood with respect to those parameters, then adds an amount proportional to the gradient to the parameters, moving up the surface of the log likelihood function. The size of the step in the gradient direction is dictated by the second derivatives. It takes bigger steps when the second derivatives are small, so that the gradient is a good guide, and small steps when the curvature is large. Hmm. Think I explained it the other way around. Wait, why does that not make sense? Is it that the gradient is not changing much here, but it is changing much here? Or I'm talking about curvature, so it's really not about this IC. You want to take, I should draw a good diagram for this. So what they said, okay, to work backwards, like small steps when large curvature. That is what he said, right? Small steps when large curvature, yeah. And big steps when small curvature. So large curvature, here is small curvature. Yeah, okay. I guess that's a good intuition. So you want to take big steps here because you know the curvature is large. Oh no, wait. You want to take small steps here. Oh, okay. Maybe I'm, yeah, is that what? Yeah, I don't know exactly what this was saying. I thought I did, but clearly I don't.
Isn't that
Small step.
you take a big step when you're really far from the local minima, and when you're close to the minima, then you start taking small step.
This is true, but I'm thinking of how minima relates with curvature in the graphical sense. So like a minima could be this, or a minima could be this. So like how does this relate to big steps, small steps, and I'm trying to build a good intuition. So like I agree with what you're saying, and that's perfect.
Is it
But like my
Swapnil, is it
Yeah.
based on like a when the gradients change their direction, like how they are increasing or decreasing? So based on that, we take the steps. So in second order derivative, we get a rate of change. So when the rate of change is like of opposite signs, maybe like based on that we decide. So for like inflection point, something like that way.
So originally that's what I was trying to figure out. Like all of you are saying the right things and I buy that, but like I'm just trying to get a sense from the graph, like is this gradient change faster or is this gradient change faster? I guess this is a faster rate of change. So large curvature means large second order derivatives. It takes bigger steps when the second derivatives are small. So bigger steps when small curvature. So second derivative is small, right? Which means small curvature, which which is this, I guess, because this is small curvature. And then this when there is large curvature. Okay, I'm confusing this definition of curvature. So this is a large curvature because there's a lot of change, like it goes from positive to negative, negative to positive. No, the slope is changing positively here, and slope is changing negatively here because this is a. I shouldn't be saying slope is negative here and slope is positive here. So there is a lot of change versus there is not a lot of change here. Um, but again, like yeah, I need to get a formal intuition. It's a very hand wavy way of saying this, but yeah, I mean, you guys understand it better than me, so I guess mission accomplished. Um, and so this is like Newton's method where you need to take the second order derivative in order to monitor the rate of change of the gradient. And like I understand that, I'm just like struggling with building that curvature on the graph and what it means. But I guess you would want to move faster here versus much slower here because like you might miss the minima if you take larger steps. So that idea is clear that everyone's on board with. It's just this sense of is this curvature more, is this curvature more? That I don't know. Okay. So in the sense that you define curvature with second order derivatives, I guess that is yeah, that's what I'm missing. Like curvature and like I guess second order is the same thing. Ah, sorry. Shouldn't harp on that. Um, so what we did with logistic regression is we built a model for P for every xi. I shouldn't say beta, I should say theta. Theta is equal to beta, not L beta. Um, and we use this model to fit y. But now because this is a per x model, that means this variance. So if g of p is equal to beta naught plus x beta, then p is equal to g inverse beta naught plus x beta, which means this variance can be different for each x and in fact will, because if x varies then this function varies and this variance varies. Which means we have to do a weighted least squares like we saw in one of the previous chapters, where for those who missed out on those, like we haven't gone through chapter 8, 9, 10, 11, but 8, 9, 10, but the idea was you have made this assumption of fixed variance noise throughout your data set in regular linear regression, where you say that, okay, my noise is drawn from this normal 0, 1, but what if each your noise is a function of x? Like what if x determines this mean, and like which means each the noise for each data point is different, right? So if I've said this before, the residuals might have structure, which means the residuals have some pattern. And you need to account for that, because otherwise in linear regression you're making this assumption that this noise has no pattern, it is just a randomly drawn noise from this fixed distribution. And because of that, instead of just doing least squares, you have to weight some data points more than other data points. So you will fit a curve, then you'll say, okay, some points are very off, they probably have more noise, then we should weight those points less because I don't care about them because I can't fit them. And then these other points that I'm already fitting well, yeah, well, I'll try to fit better on those compared to these high variance points. And that is, in a very hand wavy sense, this idea of weighted linear regression, where you associate weights which are inversely proportional to this noise variance. So the higher the noise variance, the less you want to weight that point because you can't fit it. So um, weighted least squares regression, weighted linear regression, least squares regression. The problem with y being either 0 or 1 um, um, results in this g of y being either minus infinity or plus infinity. We will evade this using Taylor expansion, where and this part is a bit unclear to me. So g of, if y is 0 or 1, then g of y, which is what, um p is 1 upon 1 minus e raised to minus x plus beta. This results in minus infinity or infinity, or what are they saying? I don't, yeah, I'm not sure about what they were saying, but the idea of evading this minus infinity or infinity problem is to use a Taylor expansion. Taylor expansion, if you remember, was this idea of, if I know this, the value of a function at this point, then I can assume it's roughly stable around this point and therefore like approximate the value of the function near that point. So that is Taylor expansion, and it allows us to say that g of y at y is equal to p is given by g of p plus y minus p times g dash of p. So this, um, yeah, that's Taylor expansion for you at a point y is equal to p. Okay. Um, and let's say this is z. So let's say this is our effective response variable, because now this is an approximation which is made because we want to avoid this problem of g of y going to either minus infinity or infinity. Um, I'm fairly sure I'm missing something very simple. So if anyone can tell me what I'm missing where this minus infinity or infinity arises, I'd be very grateful.
It comes from like just above the formula for g of p is given of log of p of 1 minus p. And
Ah, okay, right. And log, okay, cool. So if you put g of y as 0, then you get log 0. Okay. So if you put y here, thank you so much. If you put y here, you get log y by 1 minus y. If you substitute y is equal to 0, you get log 0. If you substitute y is equal to 1, you get log 1 by 0. So like both of these are undefined and therefore minus infinity and infinity. This is minus infinity, this is plus infinity. So yeah, thank you so much for that. Um, I really don't know if the best way to make these notes is to leave my random shit inside or not, but I will try to not leave it. Okay, so we bypass that by using a Taylor expansion, and so our y function will reduce to our g of y function, or our effective response variable z will now be of this form, and that avoids this minus infinity plus infinity problem. Um, and notice that if we got the coefficients right, then expectation of this is equal to p. um, this conditional mean is equal to p. So y minus p should be mean zero noise, because this goes to zero. Expectation of this term goes to zero. Um, so yeah, in other words, this is a linear function of x plus mean zero noise. This is our excuse for throwing away the rest of the Taylor expansion. So the Taylor expansion goes on infinitely. So there is a g of p term, there is a y minus p times g dash of p term, there is a y minus p square by 2 factorial times g double dash of p, and it, to make it more precise, y minus p cube by 3 factorial times g triple dash of p, and so it goes on like this. So it is an expansion, but we are cutting it off here, saying these terms really don't matter, um, because they're too tiny. And in this case, we are saying because this is actually a linear function of x plus mean zero noise, therefore these terms are not going to contribute. Um, Even though we know that the discarded terms are infinitely large. So like, um, we know that they will cancel out. And so this is plus, sorry, this is plus, this is minus, this is, I thought the odd ones were minus. Huh. Anyway, okay. So yeah, that's this idea of Taylor expansion and why we can throw away the rest of the terms. So the second thing we want to know is about this variance of this, the estimator that we have built. So the variance of our effective response is equal to g dash p squared times variance of p. So variance of noise per data point, gives us weights of data points, inverse noise variance. This VP term is coming from this iteratively, is coming from the variance of the noise. No, I don't know why I wrote that here. So excuse me. That noise doesn't have constant variance, but we can work it out. I'm not sure why I wrote this variance of noise per data point dot 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 gives us weights of data points inverse noise variance, because I said that before when we were going to weighted least squares and how. I guess I just wrote it for this part where this weighting thing comes from this variance of the noise, where because the noise variance is now dependent on x. Or yeah, I guess that's probably why I mentioned it. So g dash of p squared times variance of p, and now we have this variance of our effective response. Okay, so we want to, solve this transcendental equation that we had, by using this technique of numerical optimization that relates to Newton's method. And how does it relate to Newton's method? He's actually given a nice explanation where if you're going for, and this, um, assumes a bit of knowledge about distributions, but I'll make it clear. So the two key points are as follows. First, the gradient of the log likelihood turns out to be the sum of the zi xi, which is in equation 11.12. Oh boy. So this is your, summation zi xi sort of, because zi is an approximation to this. Uh, I shouldn't get into this. Yeah. So I gave some helpful methods about that. There is a good discussion in the footnotes. Please look it up. It is very straightforward, and it is important to like connect this variance of p to the, second derivative, which is this. This is what we use in Newton's method. So yeah. Anyway, like the idea is just that okay, we're doing similar things just in different ways. And so iteratively we do our weighted least squares, and by iteratively what do we mean? We don't know the correct parameter estimate, so we start with a guess about the parameters, use it to calculate this effective response variable. Then we calculate the noise noise variance, which gives us the weights. Then we regress this with the new weights to get the new parameters and repeat. And this converges. This is known as iterative reweighted least squares. Fair enough. Moving on. Okay, I'll pause here for questions if there are any. Oh, I see a chat message. Oh, leave your notes. That's useful. Well, I leave most of my notes in. It's just like these little things that I feel are more distracting than really add to the content. But if there are questions, please unmute yourselves. Okay. I hope my background noise is not too much, but I can't really do anything about it. Yeah. So logistic regression is part of a broader family of generalized linear models, which is called GLMs, where the conditional distribution of the response falls in some parametric family. And these parameters are set by the linear predictor. Linear predictor was our X, these parameters are beta. And so we're saying that the conditional distribution of Y given X falls into some family of X and beta. And this is like this general form where logistic regression belongs to this family, but this is a bigger family than just logistic regression because we can specify different forms for this f of x and beta. So far we've just done um, p of x beta is equal to this log px or minus px, that sort of thing. But we can do so much more. Like we can define any sort of function. And so this general family is called the um, okay, I'll leave my note in. Um, it's called generalized linear models. Okay. What else do I want to say? Changing the relationship between the parameters and the linear predictor, so this x and beta, um, can is called changing the link function. So for computational reasons, the link function is actually the function you apply to the mean response to get back the linear predictor than the other way around. And this is interesting. So it means you apply this link function to the y and get back the x rather than the other way around. That's interesting because we discussed in another chapter that transforming x makes more sense, but I guess computationally the implementation is different than mathematically in some cases, such as logistic regression. Hmm. There are also other forms of regression besides logistic. There is Poisson regression, there is gamma regression, etc. All of these are fit by the same sort of numerical likelihood maximization. Okay, cool. Perfect classification. One caution about using maximum likelihood is that it can seem to work badly when the training data can be linearly separated. The reason is that to make the likelihood large, px should be large when y is equal to 1 and p should be small when y is equal to 0. So probability of um, um, so px, so the probability of belonging to class 1 should be low, which means it should belong to class 0 when y is equal to 0. And probability of belonging to class 1, which is pxi, probability pxi, should be large, which means y belongs to 1. Uh, okay, I'll just summarize the point. The summary was, remember when we saw those plots with like the beta, the regression all over the place, and then as we increase parameters, we got to better regression. They're just saying that if you increase the values of parameters, changing nothing else but just changing beta to like 5 beta and beta naught to like 5 beta naught, this itself turns the classifier from this to this. So it's very misleading um, to use maximum likelihood alone. So like yeah, but like this is assuming you have the right beta and beta naught in the first place. So like if you run into this problem, you're already fairly lucky. So yeah. So I think the solution to like that problem is to regularize with the norm, but I don't know if that is really the case. Okay, so stepping further, a natural step beyond generalized linear models is generalized additive models, where instead of making the transform mean a response, a linear or transform mean response a linear function, we make it an additive function of the inputs. And we've discussed GAMS a bit before, and we will discuss it a lot more later. But for now, just think of it as like the way we use non-parametrics to check parametrics, we can use GAMS to check GLMs because GAMS are a superclass. So the same way we've done our simulation and model checking, you first fit both models to the data. Well, not both. Let me draw things. So what we do is you have some data, some xi, yi. You fit a generalized additive model, fit a GAM to the data. Sorry, fit a GLM. Right? GLM is a subclass. Fit a GLM. Now you simulate data from this GLM. You say I simulate some data from this GLM. Now I fit a GAM to that model. Um, and I try to test like, is this a better fit, worse fit, uh, better fit or no? I mean, what I want to check is, will this on average fit better? Again, like I'm stepping aside from hypothesis testing, but there's really no way to do that. It has to do with p-values and hypothesis testing, and under the null and alternate hypothesis, you want to check if this is just by chance fitting better, or it is actually that a GLM is not the true model and a GAM is the true model. So yeah, it's the same way as parametric regression was checked using non-parametric regression. So the same way we used to do that. This does not mean this is parametric and non-parametric, but just that this is a superclass, this is a subclass. So we can use a superclass to test a subclass because the superclass is going to contain that model anyway, but also a lot of other models. So yeah. Yeah. So the hypothesis testing is just to check if the GAM is actually a better fit or just by chance. So is true model potentially, well, I shouldn't say linear. Um, GLM, but I guess it doesn't make it. Should be very specific about what you're saying. Okay. Model checking. So we've spoken about residuals, so I'm not going to harp on this point, but if you assume homoscedastic noise, which is fixed variance noise, there's a whole chapter on homoscedasticity. We will cover it. We have covered it for the, this is for the review people. We will cover it again. So homoscedastic is fixed noise variance, and you want to check that if noise has fixed variance, then y minus your prediction is just the residual, right? And the residual has to do with noise, and the noise has fixed variance. So if this is actually the case that you observe, but in reality this is not fixed variance, then you have to go back and say, but then this residual, then this assumption was wrong, and so I have to redo my entire fitting method to change like what I was doing. And yeah, that's how we test our residuals. Um, Different ways, like you can standardize your residuals by dividing them by the standard deviation of each individual residual. Um, but yeah, in general, your residuals should be unpredictable from the covariates. Residuals should not vary from noise, and they should have constant variance. Mm, what else do I want to say? Chapter 9 discussed how non-parametric models can be used to test parametric models. Same ideas apply to logistic regression. The minor modification that in place of the difference in mean squared errors, we should use a difference in log likelihoods. And I believe we have discussed this before. I just can't remember which chapter, but there's this L of something minus L hat of something, and I forget exactly which chapter this was, but it is there before. Because So now we want to talk about calibration, which has to do with this uncertainty and this probability. So your model should output the right probabilities for y, like your y belonging to a certain class, or because you're not going y belong to one, or y is equal to one. Sorry. Um, yeah, you want it to be the right probabilities, but you don't know that it will be. So what you do is just calculate the observed relative frequencies, and by the law of large numbers, this, if you have enough samples, this should converge on the true probabilities. um, in practice, each case often has its own unique probability. So P of xi given theta, this will vary with each xi. So we can't really just say that, this all of these have the same probabilities. Like you won't have multiple xi's being the same. But if the xi's are like reasonably close, then the pi's will be reasonably close. So you can take this interval p plus epsilon, and then say, okay, within this range, this is the predicted probability. So hopefully the data exhibits the same pattern. And a second option is to use this scoring rule to calibrate your model, which is a function of the outcome variables and the predicted probabilities, which attains its minimum when and only when the predicted are calibrated. So it's like this, um, um, I can say the squared difference, um, mean squared difference between the predictions and your targets. Or you can use the normalized negative log likelihood. Um, Again, like it's just like the score function, which is typically used to check if your model is calibrated. Okay. And at the end of the day, it's like, of course, you want to do that for your test data, but like people don't even do that for their training data. So he's saying like even something like on your training data is better than not testing it at all. So yeah, try to calibrate your models. Okay, so now he gets into this toy example
I've
where,
got one question.
go ahead.
Yeah, is the negative log likelihood is the price score, or or are they two different things?
I think he's taking a normalized version. So this sample thing is what he's taking, but yeah, it uses the negative log likelihood. So it is a version of the same thing.
And negative log likelihood is a cross entropy, isn't it? It's the loss function that we're trying to minimize.
That is true.
So why it's using a different term?
This is a question that I ask a lot. I honestly don't have the answer for it, and I don't know like why. I don't know why your data is called the data, the covariates, the predictors, the explanatory variables, like features. Uh, it's just like it's how it works, I guess. Like multiple different people discover the same thing and rediscover the same thing. So like it's just a naming thing, I guess. Yeah, I don't have a better answer than that. But clearly it is using the negative log likelihood. So it is the same thing. But I guess it was discovered in a different context or used in a different context, so they named it differently. And to his credit, he mentioned historically the oldest. Yeah. Okay, so he gets into two toy examples that I'm not going to cover in detail, mainly because I read through all of them and they are exactly the application of the theory that he describes before. So it will be good if you could read this and like understand it from like not like what the code is doing, but rather what the procedure is. Because like we said, you fit a fit a GLM, fit a GAM, simulate from the GLM to fit the GAM, and then check the p-values to say if the GAM is the true model or if it is the GLM and the GAM is just randomly fitting better. So yeah, this example works through these things, walks through these things and works through these things. So it's nice. But yeah, I don't think I want to say anything more about that. This is the example. This is the code for it. It's really nice. Like if any of you are interested in R, I'm happy to do a tutorial. I don't know a lot of R, but like I know a bit of R. So yeah, the takeaway is basically this, that in this experiment, you find that the amount by which a GAM fits the data better than logistic regression is pretty near the middle of the null distribution. So it really did come from a logistic regression. Never mind. Too complicated, too much jumping over details. So another example that comes out with respect to like a proper data GAM fitting what the question of interest is, like the task of interest, like some caveats about it, how to use the fitting, how to interpret the parameters. Nothing like that isn't covered in the theory exactly. So we are good with this. What he comes back to is, where did this go? I don't, yeah, I think reading through this is the best thing you can do, because there is nothing like that's theoretical about this. It's just like comparing these things, like what happens with the GAM, what happened. I shouldn't highlight this actually. It's not like important, but it's just nice to have a worked out example of what we discussed in great detail, including some things that are not intuitive, but need to be tried out to do. So in this case, like there is some sort of problem with the logistic model, and he walks through like how we actually diagnose this, how we test it, and like looking at it, figuring out what to do. And he nicely introduces like this dummy variable, so that you want to fit a model to all of the data, but you want to give it enough flexibility to fit the data well. So he introduces this dummy variable, just in order to allow it to fit the rest of the data well. So you treat zero as a special value, by giving access to that dummy variable. But this changes things, and now like yeah, it just read through it. It's fairly straightforward. If someone has read through it and you have specific questions, I'm happy to take those. You can also always post on the channel, just for everyone's benefit. And this, the last part of the chapter is just that he says like we've just taken y in 0 and 1, but this could potentially be 0, 1, 2, 3, and so on and so forth. And all that changes is that instead of beta naught plus beta x, now we have this index c, where this is like a per class probability. Oh, sorry, per class offset and vector. So yeah, that's it for the chapter. Um, Again, like I would emphasize everyone trying out at least one question, and just post on the channel which question you try out, so people don't duplicate your effort. But yeah, I can take questions about stuff now if there are any.
I have one general question.
Go ahead.
For the logistic regression, like if we're using cross entropy loss function, or what they call it as negative log likelihood, we
Mhm.
can get the probability distribution of the prediction, so we can estimate the uncertainty. Now I'm wondering, if we will use a regression problem, then how are we going to get the probability?
If you have a regression problem, how are you going to get the probability?
Yeah. How are we gonna then do the uncertainty estimate?
Yeah, that's a great point. I don't
Maybe it will come later, I think.
if you have a regression problem, you predict your y's from your x's. How are you going to get the uncertainty of your estimates? One
Yeah.
way to do that was we checked, yeah, for you it will come later because we checked bootstrapping, where you subsample from your data and you fit multiple different models. When you say subsample, if I have like 100 data points, I fit it on 50 at a time, and I sample those 50 like randomly. So like I try to fit models to subsets of my data and then see how much my estimates change. And so that gives you some standard errors on, okay, if I subsample, like if I repeat the subsampling procedure 1,000 times, and like each time I fit a different model, right? Because there are different data points. So like it will affect my estimate in different ways. That allows me to get some sort of uncertainty estimates even for a regression model.
Right. Okay.
That
Thank
isn't exactly bootstrapping, but that is the underlying principle of bootstrapping, where you have one data set. So we'll get into the details later. But yeah, that sort of procedure is common in statistics, where in order to obtain confidence intervals, you just run something multiple times. It's modifications of your data with subsets of your data set.
you. Right. Okay. That makes sense. Thanks.
Yeah, sometimes you also like all the time you also have to ask yourself what is the best you can do, because sometimes you can't do anything. It's just it is what it is and you have to live with that. And in those cases you have to be very clear about what assumptions you're making. um yeah, other questions? Okay, seeing none, I will first stop the recording.